In this video, I want to talk about finding the mass of a solid and the center of mass of a solid. And I need to distinguish the difference between mass and center of mass here. Mass is the amount of substance that is present, regardless of the volume occupied. For example, I could have a disk with a mass of 1 milligram that is extremely thin and in the shape of a circle, or I could have an irregularly cut thin sheet with a mass of 1 milligram. In both cases, the mass is exactly the same, but the volume could be significantly different. If we have a very flat circular disk of uniform density, we can easily agree that it would be a simple matter to balance this disk on the tip of a pencil, provided I could put the disk on the tip of the pencil so that the pencil supported the disk at the exact center of the disk. Now, on the other hand, if I had this flat piece of material that's been cut into an irregular shape, I might be challenged to find a point where I could balance this by placing it on the tip of a pencil. The total mass might be the same in each case, but the difference is the distribution of the mass isn't. In order to balance the mass on the tip of my pencil, I have to be able to position my pencil at the point that we call the center of mass. This is the point from which all distribution of mass throughout that solid is equal in all directions. Now, I may have a mass of a system. Often we consider a whole mass as a system of small pieces of mass. This makes it easier to do my calculations. It also leads to something called the playground principle. If two people of masses m sub 1 and m sub 2 each sit at distances d sub 1 and d sub 2 respectively from the pivot of a seesaw, then if m sub 1 d sub 1 is equal to m sub 2 d sub 2, the seesaw will be in balance. And we could treat this as what I call a two-mass system. The point where the pivot is located, where the seesaw balances, is called the center of mass for the system. In order to state where the center of mass is, we need to impose a coordinate system on this system of masses. And we can put our origin wherever we want it, but we have to A, define my center of origin, and B, we need to choose it carefully. The choice of where I place my origin in this system of masses can make my life easier or harder. So let's talk a little bit more about center of mass. Our system of masses m sub 1, m sub 2 are located at distances d sub 1 and d sub 2 from some pivot that can be generalized with an imposition of a coordinate system. So I'm going to set up this number line here, and I'm going to define the origin right in the middle at x is equal to 0. I'm going to place my m sub 1 mass at a point that I'm going to call x sub 1 that sits to the right of x is equal to 0. I'm going to place my m sub 2 mass at a point that I call x sub 2, and this point sits to the left of 0. In order for these two masses to be balanced by a pivot, my pivot has to be located at the center of mass for the system, and I'm going to give that coordinate the designation x with a bar over it. So my center of mass, x with a bar over it, is going to be located so that d sub 1 is the distance between the center of mass and where mass 1 is located, and d sub 2 is the distance between the center of mass and where m sub 2 is located. In this case, x sub 1 is greater than x sub 2. We're talking about the distance. And x sub 1 is also greater than my coordinate for my center of mass. So the distance of m sub 1 from the balance point will be given by d sub 1 is equal to x sub 1 minus the coordinate for the center of mass. X bar, the coordinate for my center of mass, will be greater than x sub 2, so that the distance of m sub 2 from the balance point will be given by d sub 2 is equal to x bar minus x sub 2. And now I can write an equation, m sub 1 times x sub 1 minus x bar plus m sub 2 times x bar minus x sub 2 will be equal to 0. It has to be equal to 0 in order for this thing to balance. When I solve for x bar, I get x bar is equal to m sub 1 x sub 1 plus m sub 2 x sub 2, all divided by the sum of the two masses m sub 1 and m sub 2. In this expression, the product of mass times position, m sub 1 x sub 1 and m sub 2 x sub 2, these are called moments about the origin, or just moments. My center of mass in a system with more than two masses can be generalized to n objects or masses, each having masses m sub 1, m sub 2, m sub 3, and so on up to m sub n, that are located at the coordinates x sub 1, x sub 2, x sub 3, and so on up to x sub n, respectively. The center of mass condition then becomes m sub 1 times x sub 1 minus x bar plus m sub 2 times x sub 2 minus x bar plus m sub 3 times x sub 3 minus x bar, and so on up to m sub n times x sub n minus x bar is equal to the sum from k equal 1 to n of m sub k times the quantity x sub k minus x bar, which is equal to 0. Solving this equation for the center of mass gives me x bar is equal to m sub 1 x sub 1 plus m sub 2 x sub 2 plus m sub 3 x sub 3, and so on up through m sub n x sub n, all over the sum of all the masses m sub 1 plus m sub 2, and so on up to m sub n. I can write this in sigma notation as the sum from k equal 1 to n of m sub k x sub k divided by the sum from k equal 1 to n of m sub k. I want to work an example using this idea of moments in center of mass. I want to sketch the following system of masses on a number line and find the location of the center of mass. I'm given m sub 1 is equal to 8 kilograms located at x is equal to 2 meters. M sub 2 is equal to 4 kilograms located at x is equal to negative 4 meters. M sub 3 is equal to 1 kilogram located at x is equal to 0 meters. I construct my number line and I place m sub 1 at 2 meters to the right of my 0. I put m sub 2 at negative 4 meters, and this is to the left of x is equal to 0, and I put m sub 3 at 0 meters, right in the middle of my number line. Using my formula for the coordinate x bar of my center of mass, I have x bar is equal to the sum from k equal 1 to 3 of m sub k x sub k over the sum from k equal 1 to 3 of m sub k. This tells me x bar is equal to 8 times 2 plus 4 times minus 4 plus 1 times 0 over the quantity 8 plus 4 plus 1, which is equal to 0 over 13, or 0. This tells me that my center of mass is located at the point x is equal to 0, and that's exactly where my point m sub 3 is located. Now I want to extend my conversation into thinking about continuous objects in one dimension. In the prior example, I had discrete objects placed at specific points on my number line. Now I'm going to consider a long, thin rod or wire with a density of ρ that varies along the length of the rod. The density has units of mass per unit length, for example, a gram per centimeter. The key here is that this is a long, thin rod or wire. That means that the only dimension in which my density matters is in the length. So I'm going to set up my wire, and I'm going to say that the left end of my wire is at the location x is equal to A, and the right end of my wire is at x is equal to B. And I'm going to put a pivot point beneath my wire at some position. I can now slice my rod into n small pieces of mass that are each delta x wide, and delta x is given by b minus a divided by n. I dice up my rod, and I say that x sub 0 is equal to a and x sub n is equal to b. Then I have x sub 1, x sub 2, and then somewhere down that rod I've got x sub k as one of the locations at one of the slice marks I've made in my rod. This is my x sub kth interval that is delta x wide. I can see that x sub 1 is equal to a plus delta x sub 2 will be equal to a plus 2 times delta x sub 3 will be equal to a times 3 times delta x, and so on. So this means that x sub k is going to be equal to a plus k times delta x. This means that my mass at the x sub kth interval is going to be given by m sub k is approximately equal to my density function rho evaluated at x sub k times delta x. Now I'm going to let delta x go to 0 and n go to infinity. This means that my center of mass can go from an approximation using a Riemann sum to an equation involving integrals, so that my center of mass coordinate x bar is going to approximately equal the sum from k equal 1 to n of rho of x sub k delta x times x sub k divided by the sum from k equal 1 to n of rho of x sub k delta x. I'm going to take the limit as delta x goes to 0. We assume the rod has a non-zero mass and that the limits in both the numerator and denominator exist. This allows us to use the limit rule for quotients, so that my limit becomes the integral from a to b of x times rho of x dx over the integral from a to b of rho of x dx. This is a model for a rod of continuous density, where the density is not necessarily constant over the entire rod. If we had a rod with two different materials that meet at an interface, we would get a discontinuity, and we would have to take that into account. So now we want to formalize the idea of center of mass in one dimension. If we let rho be an integrable density function on the closed interval from a to b, which represents a thin rod or wire, the center of mass will be located at the point x bar, which is equal to capital M over little m, where capital M gives me the total moment of the rod and little m is the total mass of the rod. Capital M is equal to the integral from a to b of x times rho of x dx, and little m is equal to the integral from a to b of rho of x dx. Notice that the difference between these two integrals is a factor of x. The moment involves the factor of x, the mass does not. Let's work an example. I want to find the mass and center of mass of a thin rod with the density function given by rho of x is equal to the piecewise defined function that tells me my density is x squared if 0 is less than or equal to x, which is less than or equal to 1, and density is equal to x times the quantity 2 minus x if 1 is less than x, which is less than or equal to 2. This is a discontinuous mass density, but we can still work on it by breaking it up over two continuous subregions. So my mass is going to be given by little m is equal to the integral from a to b of rho of x dx, which is equal to the integral from 0 to 1 of x squared dx, plus the integral from 1 to 2 of x times the quantity 2 minus x dx. This gives me x cubed over 3 evaluated from 0 to 1, plus the quantity x squared minus x cubed over 3 evaluated from 1 to 2. I plug in those limits of integration and simplify, and I get 1. Now I want to find my total moment. My total moment is capital M, and that's given by the integral from a to b of x times rho of x dx. This is equal to the integral from 0 to 1 of x cubed dx, plus the integral from 1 to 2 of x squared times the quantity 2 minus x dx. I do the integration and I get x to the 4th over 4 evaluated from 0 to 1, plus the quantity 2x cubed over 3 minus x to the 4th over 4 evaluated from 1 to 2. I plug in those limits of integration and simplify, and I get 6/7, so that my center of mass is given by big M over little m, which is equal to 6/7. Now you get to try it. Pause the video and find the mass and center of mass for a long thin rod with the density function that's given by rho of x is equal to 2 plus cosine x, for 0 is less than or equal to x, which is less than or equal to pi. When you're ready, restart the video to check your understanding. I first need to compute my mass. Little m is given by the integral from a to b of rho of x dx. My limits of integration go from 0 to pi, so I have an integral from 0 to pi of the quantity 2 plus cosine x dx. I integrate that and I get 2x plus sine of x evaluated from 0 to pi, which gives me 2 pi. My total moment is capital M is equal to the integral from 0 to pi of x times a quantity 2 plus cosine x dx. I integrate, I get x squared plus x sine x plus cosine x evaluated from 0 to pi. I plug in the limits of integration and simplify to get pi squared minus 2. My center of mass is therefore given by x bar is equal to pi squared minus 2 over 2 pi. This is how we can work with mass and center of mass in a one-dimensional system, whether it's a system of masses or a continuous mass with a given density function. Be sure and let me know if you have any questions.